Greetings and welcome to the United States Transhumanist Party Virtual Enlightenment Salon. My name is Gennady Stoliarov II, and I am the chairman of the U.S. Transhumanist Party. Here we hold conversations with some of the world's leading thinkers in longevity, science, technology, philosophy, and politics. Like the philosophers of the Age of Enlightenment, we aim to connect every field of human endeavor and arrive at new insights to achieve longer lives, greater rationality, and the progress of our civilization.
Aging is a natural process, but it's a process which hurts our health and well-being. We are lucky to have longevity researchers developing rejuvenation therapies. Welcome to TransVision 2025.
So our next speaker is Spain's National Cancer Research Center. She's the director of that, and leading telomere research at the Heart of Aging and Disease. Not only that, Maria Blasco is also one of the 5 co-authors of the article of the hallmarks of aging. At that time, it was the 9 hallmarks of aging that was written in 2013. I'm sure all, if not most of you, are aware of the 9 hallmarks of aging that was written. It's the most searched article when it comes to longevity. And of course, now 3 more have been added. So we have 12 hallmarks of aging at the moment. So Maria Blasco is joining us to talk more on the topic. So please give it up for Maria.
Thank you very much. Thank you very much for the invitation. It's a pleasure to be here. So we all know here, I think, that in order to be able to prevent and to cure the majority of the diseases that kill us associated with aging, we know we have to understand aging at the molecular level. And one of the causes of aging, the one I have been working with for more than 30 years now, is the shortening of structures that protect our chromosomes that are called telomeres. In this review that was mentioned before, we consider this shortening of the telomeres as one of the primary causes of aging because it can lead to other causes of aging. When the telomeres become critically short, this leads to other well-known causes of aging. So telomeres shorten associated to cell division, and this happens all the time in our organism in order to regenerate tissues, and this is what can lead ultimately to these other causes of aging and to tissue aging. Recently, we have reviewed these hallmarks and added 3 new hallmarks, as it was mentioned, but I wanted to bring to your attention that if there was nothing to compensate for this telomere shortening, life would not be possible. It would be not possible to maintain the species. And in fact, there is an activity called telomerase. It was discovered by Carl Greder and Liz Blackburn that is able to elongate telomeres. So telomerase in mammals, for instance, is activated in the pluripotency stages of embryonic development, and there it resets telomere length, and the new individual will have to live with these telomeres. However, when we are born, telomerase is shut down in the majority of tissues, and this causes this progressive telomere shortening as we live, as we age. And we know that telomere length is rate limiting in humans because there are mutations in telomerase or other genes that are important to maintain telomeres. Then these individuals are going to have a shorter lifespan and are going to develop a number of diseases called telomere syndromes. So we know this tells us that telomere length is rate limiting. But also, even if you are not mutant for telomerase or for any of these proteins that are important to maintain telomere length, we also know that there is a correlation between the telomere length and the likelihood of developing a number of diseases. So telomere length has been considered a biomarker of aging, and I have to say that I founded a company many years ago. It's called Life Length, that is devoted to measure these telomeres and to see the value of these measurements as a prognostic factor for many diseases. In humans, telomeres matter, but not only in humans, in mice, and this was the I think, pioneer work that was done more than 30 years ago, and that I contributed to that, showing that really short telomeres are sufficient to cause aging, and this was demonstrated by generating mice that lack telomerase. We could demonstrate that these mice age because of telomere shortening, but also later on, we also show that if we are able to maintain telomeres long for longer times in mice, again, doing transgenic mouse models for telomerase, we were able to show that not only short telomeres lead to aging, but if you maintain telomeres longer, this delays aging. And I think this shows the importance of telomere length for aging. But not only in humans and mice, if something is important, really has to be conserved in evolution, it has to matter in evolution. And we did recently, well, not so recently, a work by seeing whether any parameter associated to telomeres could explain actually longevity throughout different species. And in this case, we did a collaboration with the Zoo of Madrid, and we look at species of birds and mammals. Birds and mammals are very distant in evolution. And we found that the telomere length at birth, it does not correlate with longevity. We already knew that from mice and humans. But we found that the rate of telomere shortening could be adjusted to a mathematical function called power law, and it could predict the longevity of a given species. So we found, for instance, that elephants and flamingos, they are very distant in evolution, but they share the same rate of telomere shortening and they share the same longevity. So here, an example of an epigenetic factor, the rate of telomere shortening, which is more important than genetics to explain longevity. So what would you do if you have short telomeres? How can we use this information to develop treatments for diseases associated with aging? First of all, we did a proof of concept to see whether by activating telomerase we could delay aging, and this is not a transgenic mouse. In this case, we use gene therapy. We use adeno-associated viruses to deliver telomerase into adult mice and to see whether this was sufficient to delay aging without causing any deleterious effects in mice. And this was published already many years ago. But we show for the first time that a therapeutic treatment, in this case telomerase gene therapy, could delay many different conditions of aging. In fact, there was no deleterious effects because the mice actually live longer, both when we treated with telomerase at the 1 year of age or 2 years of age. Cancer, which is something that of course worried us because cancer cells have the ability to maintain telomeres, and this is because they activate telomerase aberrantly, was also delayed, and the explanation for this is that the short telomeres lead to chromosomal instability, which is also at the origin of cancer. So it's clear that this telomerase gene therapy could be a promise for the treatment of different degenerative diseases of aging, and throughout these years, my lab has been focusing in generating mouse models for these diseases and demonstrating the therapeutic value of this telomerase gene therapy. So we first showed that in infarct mouse model, and we show a therapeutic effect of the telomerase gene therapy. Then we have been focusing also in the so-called telomere syndromes, which are diseases associated to very, very short telomeres. And we showed that this telomerase gene therapy had a therapeutic value in aplastic anemia, which is one of these telomere syndromes. And more recently, and I will be telling you about that mainly, we have been focusing in pulmonary fibrosis, which is one of the most prevalent telomere syndromes. Not only pulmonary fibrosis can be originated directly by mutations in telomerase of telomere genes in the familial cases, but it's now estimated that about 50% of the cases of pulmonary fibrosis could be associated to the presence of short telomeres. So this, for us, became a paradigmatic disease to prove the therapeutic potential of this telomerase gene therapy. And we have been also working in kidney fibrosis and liver fibrosis, as you will see. So the idea is that when there is damage when the telomeres are short, this leads to the lack of ability of the lung to regenerate upon damage, because short telomeres impair regeneration. We have shown that, and many groups have shown that. And because of this lack of regeneration, then you have this inflammation, fibrosis, and this is a terminal disease. The treatments that we have now in the clinic, they do not cure patients, and we think they do not cure patients because the problem remains there, which is the presence of short telomeres, which impair the ability of lung cells to regenerate. So one of the questions we had is, which cell type is the important one? Which cell type telomeres matter the most? And for that, we had a collaboration with AstraZeneca in the US, and we identified that by generating knockout models in different cell types in the lung in which we induce telomere dysfunction by removing one of the telomere binding proteins or sheltering. So we induce telomere damage, let's say, in different cell types in the lung. And we saw that the only cell type, the relevant cell type, was the alveolar type 2 cells. So this is important for us to know that we should target telomerase to this cell type. This is the cell type that matters, let's say. We have been in preclinical models, we have shown that we target telomerase to these alveolar type 2 cells in the lung in a mouse model of pulmonary fibrosis that we have developed, that is a combination of short telomeres and a damaging agent to the lung. We show that in the mice where we have diagnosed fibrosis and we treat with the empty vector, the fibrosis progresses, but in the mice that we diagnose with fibrosis and treat with the telomerase vector, the progression is stopped or is reversed. So this is telling us that there is a therapeutic value of this telomerase gene therapy in this mouse model. If we isolate the alveolar type 2 cells that have been treated with telomerase, we can see that there are decreased inflammation and decreased DNA repair pathways, and they have active telomerase, indicating that we are reversing, let's say, the cellular events associated to short telomeres. Of course, we are worried about cancer. I mentioned that before. We have no evidence that this telomerase gene therapy can lead to more cancer in the longevity study that I showed you before. But nevertheless, we wanted to push and see what will happen in the lung if at the same time that you put telomerase, or before you put telomerase, you activate an oncogene, a well-known oncogene that leads to lung cancer, which is KRAS. So we did this safety experiment, seeing whether by forcing cancer in the lung, having or not telomerase matter, and the results were very clear. Either if we put telomerase before or after the oncogene activation, this didn't change the number of mice with tumors, the size of the tumors, or the aggressivity of the tumors. Again, indicating on the safety of this telomerase gene therapy approach that we are using. So all this led us to think that this could have a value in humans, and that maybe some cases of pulmonary fibrosis in humans could benefit from this telomerase gene therapy strategy. And we funded a company which is called Telomere Therapeutics, and which is trying to bring this to the clinic hopefully soon. So I wanted also to tell you that, however, maybe not all patients with short telomeres, due to mutations in telomere binding genes, may benefit from a telomerase activation. And we learned this recently by studying a mutation that has been described in humans recently, which leads to pulmonary fibrosis. It's not a mutation in telomerase, it's a mutation in a protein called POD1, protections of telomere 1, which is one of the telomere binding proteins. There are some mutations in POD1 that lead to cancer, and some mutations of POD1 that this is the only one that has been described so far that lead to an aging phenotype. So we are a basic lab, and we wanted to study what was doing this mutation by generating a mouse that carries this mutation. And well, we saw that the mice had shorter telomeres, the same as the humans, carrying this mutation in POD1, and they had more telomere damage. We then thought, okay, maybe this is the same as a telomerase knockout. We are going to generate generations of this POD1 mutant and see whether telomeres shorten, like in the telomerase knockout, and this is what we saw. So it seemed that this mutation was recapitulating a telomerase deficiency. As you can see here, this is in the telomere length. But it also recapitulates the phenotype. So this POD1 mutant is identical to a telomerase deficient mutant, and the different generations of these two mice have exactly the same phenotypes in terms of weight, litter size, or pathologies. Is the first mutation that actually is like not having telomerase. And actually we see that if we combine both mutations, this is epistatic, so it's telling us that POD1 is somehow this POD1 mutation is affecting the activity of telomerase. And actually we cannot correct the short telomere phenotype in these mice if we overexpress telomerase. So this is telling us that in the case of this particular mutation, I'm not going to give you the details, the paper was just published, but you have a protein that is able to bind to the telomeres, that is able to bring telomerase there, but telomerase cannot work with this mutation. So this tells us on the importance of studying all these human mutations in order to select which patients could benefit from the telomere gene therapy, of course. And if I have 5 minutes, I would like to mention what we're doing with kidney fibrosis. Pulmonary fibrosis, as I said, is the paradigmatic disease for us because there are these families that carry mutations in telomerase and telomere binding proteins that develop pulmonary fibrosis. But a much more prevalent disease is kidney fibrosis, and this disease is increasing with the demographic aging. So we wondered a few years ago whether short telomeres were also at the origin of this other type of fibrosis, right? And for that, we generated a mouse model in which we saw that short telomeres were at the origin of fibrosis, because if we had normal mice and we challenged them with something that produces kidney fibrosis, nothing happened because we use a low dose. But if we have a mice with short telomeres and we use this same low dose of the damaging agent, in this case folic acid, the mice develop full-blown kidney fibrosis. So this is telling us that short telomeres are at the origin or are contributing to the origin of kidney fibrosis in a mouse model. And this was already published, and we also found something unexpected. It was also that short telomeres were contributing to plasticity changes in the cells. In particular, they were contributing to what is called epithelial to mesenchymal transition, which is a phenomenon that is at the basis of cancer, but is also at the basis of some fibrotic diseases. So this is interesting because it's telling us that short telomeres per se are able to induce these plasticity changes from epithelial to mesenchymal transition, and this may explain why short telomeres, on top of leading to chromosomal aberrations, can also lead to cancer by inducing this epithelial to mesenchymal transition. So in this case, and just to finish, to tell you that we are also trying to see which are the relevant cell types in the kidney where we will have to target telomerase. And I tell you that we have published recently that the fibroblasts or the pericytes are not relevant, because when you induce telomere dysfunction there, you don't induce kidney fibrosis in an acute manner. However, we found recently that are the epithelial cells again, like in the case of the lung, the ones that matter, as well as the basal cells in the kidney. So the epithelial cells paper was just published also, and this is just to show you that just by inducing telomere dysfunction in these compartments, in these epithelial cells, we induce kidney fibrosis. And the same happens if we induce this in the basal compartment. In this case, it's a much more severe phenotype with hydronephrosis, which is a kidney disease, and this is an interesting model for this kidney disease. But you can see also that when we induce telomere dysfunction in basal cells, we have fibrosis in the kidney. So we think that in general, these short telomeres may be contributing to different types of fibrosis in the organism, and we are, for that, also interested in studying, for instance, liver fibrosis in the lab. So I will finish here with the group in the CNIO, and I have to mention that the gene therapy was done in collaboration with the group of Fatima Bosch in the Universidad Autónoma de Barcelona, and the funding of the group, and I will finish here. Many thanks. Questions?
Thank you so much, Maria. So we have one last speaker for this session, and it's João Pedro de Magalhães, who is a chair of molecular biogerontology at the University of Birmingham. He's also chief scientific officer at the YouthBio Therapeutics, and really a genomics pioneer, decoding the complexity of aging and its translational future. So I give it up to João Pedro.
Thank you very much.
Thank you.
Thank you very much, and thank you. Thank you. Thank you, and thank you. Gracias, José, por la invitación. Un placer estar aquí en Madrid, pero voy a hablar en inglés. Hablo un poquito de español, but I will speak my talk will be in English. So thank you. Let me start with my conflicts, as you mentioned. So I'm also CSO of YouthBio Therapeutics. I'll briefly mention some of our recent work later on, but I'm also an advisor and consultant for a few other companies and investors. So I have some conflicts of interest. And as we've heard already, of course, we have a major challenge of this silver tsunami of the aging population, which tackling aging is a priority. And I mentioned curing aging here, actually, because I think we should be ambitious in what our long-term goals are. We should aim to, ultimately, if you work on Alzheimer's disease, you want to cure Alzheimer's disease. Perhaps that's not possible now, and therefore you try to improve the lives of patients for now, but the ultimate goal is to cure Alzheimer's disease. And same for aging. Our ultimate goal is not just to improve lives, of course we want to do that, but also to develop interventions that slow and eventually stop and reverse aging. I'm not saying that's going to be possible anytime soon, and I'm saying that's going to be possible with current technologies, but that is the long-term goal. And interesting enough, it raises a number of ethical issues, which I think Mahmoud Khan already mentioned today, which I think is important for us scientists to address. And I mean, one of my other hats in the Oxford Ruhiro Institute of Ethics, we've been working on this manuscript on arguing why it is ethical to intervene in aging to radically extend human longevity. And I think that's a discussion I'm happy to have with anyone. And I think it's important for us scientists in the field to have as well. Now, because as I mentioned in a previous paper, our goal is to allow people to be as healthy as possible for as long as possible, even if that long is a very long time. So, let me try. Having said that, again, I'm not saying it's going to be possible anytime soon, and that there's, I think, a lot of caveats to this. One of them is that we still have a poor understanding of the drivers of human aging. We know of a number of hypotheses. We've heard a great talk from Maria Blasco just now on telomeres. We know of DNA damage, epigenetics, oxidative damage, mitochondria, senescent cells, and so on. So we have a number of processes, molecules that change with age, but we still have a limited evidence, empirical evidence, that these are drivers, that these are causes of aging. And so we still do not understand the processes of aging well enough. Now, and of course, this is a major challenge. Now, I would say in this context as well that I think sometimes we tend to focus a lot on the lamppost, and it's important to also be open to other hypotheses. So one hypothesis I'm interested in, what I call a software design flaw, is essentially that perhaps aging is not a result of errors. Perhaps we don't age because of molecular damage, although certainly contributes to some aging pathologies like cancer, but it is primarily a product of regulated gene programs that are regulated during developmental processes. So that's an alternative hypothesis. I don't have time to go into details, but the idea very, very briefly is that we have developmentally programmed, genetically encoded changes that start early in life and are optimized. Their trajectories are optimized for reproduction, for maturity. And the hypothesis is that this is, as a form of antagonistic pleiotropy, they become detrimental later in life. So for example, the thymus begins to involute when you're about age 3. Presumably for some biological evolutionary reason, and this continues until later in life and becomes detrimental. So it could be perceived as a software design flaw, as a detrimental process, or a beneficial process early in life that becomes detrimental later in life. Of seeing aging as, I don't like the word program, I like the word programmatic. And it fits actually, Michael mentioned caloric restriction. It fits very well because Clive McKay actually tested caloric restriction under the assumption that it will slow growth rates. Under the hypothesis that if you slow growth rates, you can extend lifespan and slow down aging, which caloric restriction does, just like rapamycin, just like growth hormone IGF-1 mutations in mice. So the major pathways we know, the major methods for retarding aging in mice, actually all of them fit this programmatic view of aging. I mean, having said that, there's still many, of course, open questions in the field. I mean, one of the things we did with a number of experts, including some of them here today, is create this list of 100 open questions in longevity and aging science to serve as a roadmap to the field, and perhaps not unexpectedly, many of these focus on understanding mechanisms of aging, understanding why we age, which I still think is crucial to then develop better interventions. And because I think we have this limited understanding of the mechanisms of aging and the theoretical basis of aging, there is still no proven way of slowing human aging. And I think part of the reason is because we don't have a strong theoretical framework to which base our interventions. Having said that, there has been advances, of course, in preclinical models, in animal models. We've heard about that today already. But I do feel, or I'm concerned that perhaps we are reaching a plateau. So Michael again also mentioned the ITP today. So what you see here are the effect sizes of longevity drugs in mice from the ITP study, which is the benchmark, the most robust and the most actually very large sample size in terms of testing interventions for longevity in mice. So you see on top it's average lifespan, and at the bottom is maximum lifespan, and that's the effect sizes of the compounds that extend lifespan in the ITP. And as you can see, they are not having such big effect sizes. It's the maximum, I think, is about 16% in terms of maximum lifespan, which is a stronger predictor of effects on aging, and that's from rapamycin, which was discovered, I think Michael showed this Harrison et al. Nature is 2009, if I remember correctly, so 16 years ago, and we haven't done better since then. So we haven't really, although we are discovering more longevity drugs, they're not really pushing the boundaries of how much we extend longevity in preclinical models. And we still haven't extended lifespan in mice more than caloric restriction, which was discovered roughly a century ago. So in a way, we're not really pushing these boundaries. Now, sometimes you can say, okay, well, but maybe my intervention improves health to some degrees. I'm not a fan of the health span approach or the health span framework. I think that, of course, we want to extend lifespan with good health. We do not want to extend lifespan in a period of decrepitude. We want to minimize suffering. We want to minimize disease. But if we are retarding aging, then there should be a lifespan effect. Ultimately, mortality is one of the principal outputs of aging, because aging increases our mortality exponentially once you reach about age 30. And that's the same in mice, only much faster. So if we are retarding aging, it should have more than health benefits. It should have lifespan benefits. So I think that's also important to mention. Now, when you look at the current focus of longevity pharmacology, these are pathways and processes that are quite largely, I'm sure you'll be familiar with this, like oxidative stress in mitochondria, targeting senescent cells with senolytics, and well, other therapeutic approaches as well, and mediators of caloric restrictions like mTOR and AD+. So these are the current focus of the main companies or the companies in the space, which it is relatively narrow. I think there is a problem that I'm concerned about, is that I think we need to be more creative in longevity biotech. We need to have a more diverse set of approaches. Again, most companies and most are working under the lamppost instead of branching out and being more ambitious and bolder, which I think we can be as a field if we want to. Now, to give one example, which I'm sure you're familiar with, this was from some months ago, this big biotech company that ran into some problems. I'm sure you're aware, or most of you should be aware, that this was Unity Biotech, based in the US, which focused on developing senolytics, these drugs that ablate senescent cells. And this is perhaps not surprising, particularly in light of the data, of the biology of senescent cells in aging. Namely the fact that it's now clear that senescent cells have normal physiological functions. I mean, we know they work as tumor suppressors and they have roles in inflammation, but it's now clear as well that they play important roles in development, in tissue regeneration, in vascular structure. There's excellent work, for example, from a group in Nice showing that if you ablate senescent cells, you can disrupt the vasculature in mice and actually shorten lifespan of the animals, even in beta cells in mice and humans. So it's now clear that senescent cells are not there. They're not like cancer cells that you just want to destroy. You cannot just destroy all senescent cells, or that will be detrimental. And unfortunately, we still cannot discriminate between harmful senescent cells and physiologically important senescent cells. And so, again, it goes back to the basic biology. We need to understand the basic biology better in order to then develop effective interventions. So, in terms of, for example, the work we're doing in our lab, a lot of what we do is in terms of developing computational systems biology, machine learning methods that tackle the complexity of biology. So I think one of the problems we have, of course, is that many things change. Many things change with age. Our body, well, our genome is 20,000 different protein coding genes. God knows how many known coding genes. So we have this massive complexity of biology that we still do not understand. But thanks to omics approaches and analytical approaches and data sciences approaches like machine learning and AI, we can gain insights and try to make sense of the complexity or tackle the complexity of biology and gain new insights to identify new drugs or new genes that are important for aging and longevity. So, I don't have time to go into. We've done a number of methods developed, but I show a very quick example of some of the work we've done in terms of predicting longevity drugs with machine learning. So, you can look at machine learning as a classification algorithm. So we tend to use what's called supervised machine learning methods, where you have a certain class of, could be genes, could be drugs, and then you look at their particular characteristics. Chemical characteristics of drugs, for example, which genes they target, which pathways they target. And then you use a machine learning method to predict new drugs with those characteristics. And so we've done this for worms, we've done it recently as well for mice. And one of the, I think, success stories is we employed these in silico methods to identify a new geroprotector, a new longevity drug called Rimenidine. Now, Rimenidine is already used in the clinic. It's an oral antihypertensive drug that, as I said, it's already approved for use, not in the UK actually, but it is in France, for example. And then we did various experiments in C. elegans, which I don't have time to show now, but it extends the lifespan in both young and old worms when you feed it at, particular 200 micromolar dosage. So we show it's a new geroprotector. We've also done collaboration with Vadim Gladyshev in Boston, and Conley Huewald. We also show that in mice, we can, it induces, when you feed Rimenidine to mice, it induces gene expression signatures or molecular signatures that are similar to other life-extending interventions like caloric restriction. We haven't done lifespan experiments in mice. That's obviously, what I'm trying to get funding to do is to do a full lifespan study. But we can argue that this is a promising geroprotector, and we can repurpose this drug for other clinical uses. I'm not showing here, but Rimenidine is actually an autophagy activator in human cells, data from David Rubenstein in Cambridge, for instance, and others, and data from our lab in C. elegans. So it perhaps could be repurposed for treating neurodegenerative diseases, and we're trying to get funding to do a small experimental medicine approach with Rimenidine. So I think it's a good proof of concept of how we can use this computational analysis to identify new longevity drugs that we then tested experimentally in animal models. So, in the last few minutes, I'll go back to some of the work we've been doing with YouthBio. So as I said, I'm CSO of YouthBio. The company is based in the US, but we then do collaborations with different labs, including primarily Alejandro Campo, one of the pioneers of partial reprogramming. Again, Michael introduced partial reprogramming. Our goal is to develop gene therapies that restore youthful profiles using OSKM. So that's our goal. And we've been doing some work on preclinical models, in particular, mouse models, as I said, with Alejandro and others. So recently, just a couple of weeks ago, we had this very positive feedback from the FDA regarding doing a gene therapy trial for Alzheimer's disease. So this would involve, you might have seen this recent news on Huntington's disease gene therapy as well. It's a similar procedure, which is essentially a brain surgery where you inject a viral vector, in our case with OSKM, in their case I think it was a DNA silencing vector, but you inject lentiviral vector into the brain during brain surgery, into the hippocampus, to then express OSKM. So that's the idea, which I think is, of course, I mean, I think again, it goes back to what I was saying earlier, that I think we need to be bolder. I mean, there are obviously less risky approaches we can take, and other companies are doing so, but I think that's the way to go, is to try to be ambitious and bold, and of course, hopefully, if this would work, then it would be transformative for Alzheimer's disease patients. And so, what I've told you is that, of course, aging is a major biomedical challenge. We're all of that. We're well aware of that. And we need to tackle aging and develop interventions for aging. But it remains a mystery of biology in the sense that we do not yet understand why we age. I am aware that we have the hallmarks of aging that Maria mentioned earlier, but those are not empirically proven. Some of them, there is some evidence, but there is no conclusive evidence that any of them are drivers of human aging. And so we need to be open to other ideas. I mean, perhaps we age because of telomeres, perhaps we age because of DNA damage. We do not know yet. There may be something else that we're missing. And so in that context, I've told you about this idea of programmatic aging, the software design flaw hypothesis, which I think has been very underexplored and underrated, which is something we're very keen to study. And I think, again, it's very important to have a strong theoretical framework and molecular/mechanistic understanding of the processes driving aging to develop better interventions. We need to be driven by the science to develop better interventions. I've told you that we are developing some longevity drugs, yes. I didn't show you, but the number of longevity drugs we're developing or we're discovering in preclinical models has been increasing in recent years, but not their effect sizes. And I think there is a real concern. So again, I think we need to be more creative in how we approach the problem of aging if we want to have major impact, if we want to extend lifespan more. I've told you some of our work on in silico computational methods, in particular in application of machine learning to identify new longevity drugs. We've actually have several results on this topic, but I showed you one example as a proof of concept, namely that rilmenidine is a new geroprotector, it extends lifespan in C. elegans. It induces similar changes in mice to, for example, caloric restriction, and it activates autophagy. So I think there's a lot of potential for rilmenidine for drug repurposing in the context of other age-related diseases. And lastly, I told you about our work with YouthBio in terms of doing a gene therapy trial for Alzheimer's disease, which is what we're currently through fundraising to try to do. Which, again, yes, I think it's ambitious, it's risky, but it's bold, and I think it's what the field needs. And so with that, thank you very much. I mean, any preprints and PDFs will be available on our lab website, and feel free to contact me if I can help in any way. Thank you very much for your time and attention. Thank you.
Thank you so much, Carl. Yes, please stay, and I'd like to welcome Maria and Michael up on stage again, and hopefully we have a talkative audience, because I'm going to start to see if the audience have any questions initially. Does anyone have any questions? Yes. Do we have a volunteer with a mic helping us? Otherwise, we have... His grim age is going down for every second he hands over the mic. Yeah, at the end. Oh, Aubrey first.
Right, since I got the mic first, wonderful talk to all of you. I arrived just in time for the second half of Michael's talk, so I really enjoyed the session. I could think of half a dozen questions, but let me just start with one for Pedro. This drug that you're now looking at, if you've already shown, or Vadim has shown, that it has the molecular signature of a CR mimetic, then why are you interested in it, since we already have CR mimetics that work perfectly well?
Did anyone...
Sorry,
no.
I didn't question, I'm afraid.
So say it again?
I think also the sound speaker here is a bit... So Aubrey, could you just...
Say it again? Sure. You're looking at a new drug, relmeladine, that has the molecular signatures of a CR mimetic, right? Why? I mean, we already have CR mimetics, so why would you look at another one?
Carl, would that be for you?
Yeah, I think I understood the question. The question was, we're looking at drugs that induce similar signatures to CRs or CR mimetics, but why are we doing that given that we already have these CR mimetics? Right, okay. So, well, because in mice, there's only a limited amount of interventions for which we have gene expression data. And so it was not just CR, I mentioned CR, but actually it's not limited to CR. There were other longevity drugs for which you can derive gene expression signatures, as well, Vadim Gladyshev did that work. And so when you look at relmeladine, for example, we can see that there is greater than expected by chance or statistically significant overlap with these longevity drugs. It doesn't mean they work exactly by the same mechanism. We don't know. I don't think they do necessarily, but it means that they are inducing longevity signatures that are similar to other longevity drugs like caloric restriction, which I think is reassuring if you at least go in the assumption that there is some overlapping processes across different longevity drugs. Does this answer the question? Kind of.
Kind of. Anyone wants to add anything? No? Okay. Thank you, Aubrey. And I know we had someone there at the end. Yes.
Too far.
Did we have a mic?
Yeah, but it's just too far.
Maybe someone
Yeah.
can pass it along.
Thank you. You were talking about gene therapy on telomeres. It has been tested just on mice. Tomorrow, in this event, Lyfe Paris is going to talk about, she has proven this gene therapy on herself. And I wanted to know your opinion on this story, on this event. There are a lot of people who are talking about pushing the boundaries of science. How far can they be pushed?
Pushing the boundaries on science, and how far can they really push?
In general, I guess the question is pushing the boundaries in science. So I think in science we have to be bold, as we heard in all the talks this morning, actually. But I think there are has to be done right through the regulatory agencies, and at least in our case, we believe fully in the telomere gene therapy as a promising way, really, to treat different diseases of aging, because we have shown that in the mouse models, and we think telomeres are important for aging because if you shorten them, then you age faster. If you elongate them, you delay aging. So there is a lot of evidence in preclinical models. At least our way to go would be to through this company called Telomere Therapeutics, try to bring this to the clinic, try to bring telomere gene therapy for the treatment of these diseases like pulmonary fibrosis.
We have another one? Yes.
Yes. Thank you all for the stellar presentations. I have a brief question for Michael Ringel. Thank you for your clarity. Michael, do you see mitochondrial decline, the loss of ATP and rise in ROS as the more fundamental overarching problem that should be integrated with epigenetic reprogramming to solve the mystery of aging faster in a 2080 way? Yes or no? And why? I'd value your most critical reflection.
Mitochondria question. Did you hear him, Michael?
I did hear the question. I have the temerity to answer the question since it's addressed to me when one of the authors of the Hallmarks of Aging is standing behind me. But as João Pedro pointed out, exact causality is still debated. I think for all the hallmarks, there's evidence that amelioration of them can ameliorate age-related disease. So I would include mitochondria as well as all the others within that. I do think the most stringent test of whether something is truly upstream in causing aging is if I reverse it, can I completely reverse age? Right? So not slow it down, not ameliorate it a little bit. Can I truly, completely rejuvenate? And the only thing that I know of that does that and it's not in the context of whole organism yet, maybe it will be, but in the context of individual cell is this epigenetic reset. So the most stringent test, I think there's only one hallmark that could pass it with existing data. I do think it's actually the upstream cause. There's still, it remains to be proven, but it's at least a reasonable hypothesis. But that's not to say that action on all of the other ones can't have value. And some of the downstream things you do around that, right? Exercise and caloric restrict and manage your sleep, all of which have value. But I think if we're looking for a true reset, we need to deal with the epigenome.
Maria, would you like to add anything? Would you like to add anything to that? No? No? One more question. Yes, we have one there.
Hello, this is a question for Michael. In order to use the rapamycin to block the mTOR protein, it's a natural molecule of the normal cell. What for do we need to take the rapamycin in order to block or to regulate or to modulate the molecule?
Rapamycin, yeah.
So I'm not sure I heard it exactly, but basically, what do we need to address mTOR as a target, in essence? So there are medicines already approved. They're not approved for use as a geroprotective. They're approved for transplant patients. They're originally actually approved for infection. They need to be tested. I'm a big believer in evidence-based medicine. If you're going to prescribe something for a given indication, whether that be slowing down aging or whatever it is, you should prove it. You should need to prove that it's safe and effective in a regulated trial-based approach. And so there has been some work done in that regard, and I hope there'll be more work done. There are 3 agents that have shown efficacy in the ITP in mice of a 10% or greater maximum lifespan extension. One of them is rapamycin, which works directly on mTOR. I think they should be tested in humans in a controlled clinical trial to ascertain whether they can address features of age-related disease.
Okay, yes, first of all, let's give it up for Michael, Maria, and João. Thank you so much for sharing your knowledge. Thank you for that. Okay, before the break, we heard about theories and the visions of longevity, where we are, where we're heading, and what's possible. Now we're going to turn more into applications, as in how does basic research really translate into therapies and interventions with real-world impact. And for this session, we have 3 really knowledgeable speakers who will talk from their different perspectives, and they'll be talking 15-20 minutes each. Then at the end, we'll have Q&A sessions as we did before. Please give it up for José Crespo. Let's give him a hand round of applause so we can get some energy in the room.
Thank you very much. I want to be especially thankful for my computational team, Lucas Zamora, Daniel Quintana, Efrain Martinez, and also João is also here. We are going to talk about the project. I'm going to make a brief presentation of the project. First of all, I would like to make a brief preview to see if we have a solid line in the previous part, so maybe we can move forward and you can see the continuity of where we're doing. We are going to discuss about anti-atherogenics, and we are going to also discuss about a new concept that we are going to introduce, which is a CellNet. We will see what is that, but later on. And finally, we are going to talk about briefly about a possibility that we will offer, which is a membership inside Regeneratics. I made a PhD in aerospace engineering, but the good point is that we have some trajectory, and I would like to know why I think it's solid. I'm very honored to say that we make work in angioregenerative that they border on different complexities of different kind of angioregenerative, for example, angiogenesis, which is different for the oncoangiogenesis, but also lymphoangiogenesis, arteriogenesis, or vasculogenesis, de novo. There are different kinds and different kind of treatments. It's different whether it's that anti-atherogenics or is, for example, pulmonary hypertension. But the good point, I'm very honored to say that someone with more than 65,000 Google Scholar citations made work similar, very similar, and I'm very honored to say that if someone with very high reputation like him did that and put his name on that, means that maybe and just maybe we are doing the things in the proper direction. And another previous one that I want to say is that by 2020, SARS-CoV-2, there were some findings about the microangiopathy. And we could see that in 2022, there was intriguing connections between the coronary microvascular disease, which is one of the main key problems with the angina pectoris symptoms in long COVID patients, which is a kind of chronic disease after the pandemic. And by that time, there was a main concept about dysautonomia. But I was very fortunate that in the Cardiovascular Institute of Spain, someone who is, for me, is very wise man, both professionally and intellectually, a scanner, decided to listen to that. And 2 years later, they found the evidences. I presented to someone who found some evidences with that. And they received the Gran Cruz de Comunidad de Madrid. Isabel Díaz de Ayuso were awarded with that. So maybe and just maybe we have an interesting line for the future. What you are going to see right now is that I found it, so that gives me the confidence for founding Regeneratics, which means bioinformatics and regenerative bioinformatics. In that future line, we have a mid goal, which is angioregenerative and immunoregenerative, which means the regenerations of blood vessels, but not only blood, but also lympho. And immunoregenerations. We plan open a hospital by mid-27 and 28 for cell reprogramming therapy. We have interesting discussions in Dubai, but also here in Spain with different actors. And the long goal, of course, is going to be, let's say, clinical rejuvenation, but you know what I mean. So I think that's the strategy. But maybe and just maybe we are not interested in direct investors. I'm going to explain politely why, because if the company, I'm fully compromised with the company. It's a personal project and I want to give the maximum quality. I have some affections after the pandemics and I'm 100% sure that I want high quality outputs of it. So maybe and just maybe direct investors could expect after multiply by 4 the value of the company to make a sell-off, and maybe and just maybe it's not interesting for the long term. But I do interest in membership program and insights projects that are highly profitable and could inject capital to the Regeneratics in the long term. So, of course, direct investors are very welcome for the size project to come into it. And well, 2025, it's been a great year. We have 1 gold medal in mathematics in the computational team, mathematics of Spain, and other medal in biochemics. We have our own know-how in anti-atherogenics. We have trademark protection in Spain, and also we are doing in the US and European Union. And we have incipient collaborators in the US and also in China with robotics labs, because we need to escalate the data for many aspects to integrate machine learning, the experimental part. And we are very honored that in a few minutes we are going to have the pleasure to talk to someone which is Dr. Pichardo, who is been a postdoc of the David Sinclair lab, and is the chief scientific officer of Legacy Lyfe, and we will discuss it in a few minutes. We will have the pleasure of having a short conversation with him. And why anti-atherogenics matters? Well, vascular inflammation is the major senescent, not the major, but let's see is one of the major senescent drivers. And we will see that. The vasculature also is the fastest in aging. And well, there is a kind of, there is a feedback between hyperperfusion and low-grade systemic inflammation, and of course cardiovascular events are the first cause of death, unfortunately. So atherogenics is a kind of ticky-type bomb. So I think that's interesting. It's not me who is saying this. They are very recent journals. You can see here that in the vascular system, the xenoproteins basically mid-age onwards and triples the xenoproteins with the rest of organs. And there is also a turbosenescence of the vascular system if you have continuous several reinfections of SARS-CoV-2. So even if you feel asymptomatic of SARS-CoV-2, the aging clock, vascular aging clock, is saying another thing, and it's top journals who say that this is very recent. We were already discussed in the past, 1 year ago, a specific microRNAs that involves in cells crosstalk conversations to reverse the atherogenics, of course, with many limitations, because this is a very early discipline, but we think it was interesting, and it's a very complex problem, not only at the patient level, but also cellular, proteomic, and transcriptal level. There is no magic pill for this. So cellular crosstalk is important, but also a new concept that I think is also important, which is CellNet. It's a kind of game with the words with internet, but what is CellNet? CellNet is actually, there is a kind of neural network, but chemically driven with all cells. It's not just a cellular crosstalk, but it's a huge coordination. And this is very important, for example, for gastrulation, or for example, for major vasculomorphogenesis, which is the major kind of, there are many kinds of angioregenerative. This is one of them. So very complex processes. We will see it a little bit later. But just to see the complexity of the problem, consider that you inject 8 anti-inflammatory agents, and if you, with the same anti-inflammatory agents, you change the distribution, you obtain completely different results for the markers. This is actually for human umbilical vascular endothelial cells, which is very common for experimentation. It's very complex, but it's a kind of a problem that you have to guess which is the right combination of a safe box, of a bolt. Which is the right combination, because there are a lot of combinations. Well, I think that maybe Regeneratics is doing a good job in guessing in the minimal number of iterations, in the minimal number of experiments, which is the solution that you have. And maybe we could be useful with this small contribution to other companies that want to make less experiments to find the gold treatment that they would require. So to give a particular, a very simplistic scenario of what I'm doing, consider, for example, these cytokines, pro-inflammatory, to drive the cell into an initial inflammatory state. And then we are trying to recover the initial state with different anti-inflammatory vector. Of course, we have some markers to see how the things are going on. The point is that after the initial inflammation, we are able to analyze the complexity of the problem. And after that, maybe you have to make a principal component analysis or another filter algorithm techniques, but eventually you perform machine learning, and in only 2 iterations, you have the 2%, only 2% of the initial inflammation, which is a clinical zero inflammation. So, of course, there are many study limitations. I'm not completely happy with that, because we have to test that we have to test it. We have to test it in vivo. This is just in silico. So it's fine, but we need experimental validation always. And the good point is that if we have enough data, we were able to do a deep learning to predict with 0 iterations the results. And in the X level, you have the number of tests, so 200 tests, and basically the results overlap, the reality with the prediction. So I think it's been a good job made by Lucas, which is here. I'm very happy with my team, by the way. And it's great, but we are very lucky to have here Dr. Pichardo. I don't know if now you can connect with us. Maybe the technical team can show the image. Let's see if we have the privilege of having the image there, maybe. Oh, thank you. Be very welcome, Israel. It's a pleasure to have you here, the Chief Scientific Officer of Legacy Lyfe, and also made a postdoc with the David Sinclair group. Thank you very much. I don't know if you can hear him. He was in the Harvard Medical School, and we are very lucky because he can do the experiments that we require. We have interesting collaborators.
I'm going to introduce myself and the company that I represent, and I'm happy to support Jose and the Regeneratics team. So we're very excited about what we can do together. So I'm going to basically present the way we're going to interact and validate Jose's model. I'm trying to share here my screen with you guys. Probably you can see it now. And I'm going to go ahead, and I'm so jealous I could be in Madrid right now sharing with you. It's an excellent audience right there. My name is Pichardo-Casas. I'm the Chief Scientific Officer for Legacy Lyfe Labs. This is a company based in Pittsburgh and Aspen in Colorado in the United States. And we decided to partner with Regeneratics and Jose's team because we are very interested in modeling not only the secretomics, which we're very interested into, which is a tool that we want to use in order to improve and extend health span in people. And using some of these models that he's developing, we're trying to fine tune, where which diseases and which to inform decision making, how we can make better therapeutics, starting in the biologics point of view. So I used to do this research at David Sinclair Lab at Harvard before, and we used to study peptides, and now we definitely are interested in the same components that are floating around in the blood and the liquids. So the case study we're trying to push with a model that Jose was describing, it was, trying to use a specific and complex structures. It could be like therapeutics as cells, it could be therapeutics as biologics, that may contain multiple, many multiple cargos. And the exosomes, which are particles that are normally released by all the cells, especially the ones that are very, very interesting are the ones that are released by stem cells. The idea for us is to profile the cargo, which are basically all the proteins, enzymes, RNA, and metabolites that are contained within these particles in order to produce data sets that we can feed into the model. And the idea for us is to, create, based on these omics and systems biology type of platforms, to create measurable state vectors, that we're going to feed into the model. So then we can identify specific levers or specific components of these particles based on how the cells that they are going to be absorbing or being affected by these exosomes. For instance, we can use in order to engineer further. So in order to do so, we have created like a three-phase type of approach in which the idea for us is to start not only characterizing the particles, but also interrogating, how their effect in specific cell autonomous assays, we can identify the effects of these particles and the responses of the cells, and then creating iterative models of proteomics and transcriptomics for the most part, in order to answer what are the changes in the cell responses. The phase 2 is actually characterized by identifying how the crosstalk between different cell types that release a particular flavor of exosomes can be affecting cells, for instance, in terms of the inflammation patterns and the reversal of such patterns. And then finally, the phase 3 is characterized how we can validate all these findings of this like a loop model in order to inform better outcomes in vivo, and particularly for measuring inflammation and atherosclerosis as an outcome. So as Jose was defining, he's aggregating sources, normalizing a common schema for all the contents in the cells that are being diseased. Then pre-registering some of the possible biomarkers and changes, phenotypic changes that are happening that we can predict based on literature and also the clinical assays and so on. And then for us, the way we can complement, his model is to identify actually these molecular changes in the phenome based on how we use our products that we're developing also here in the United States. So the idea is, by grounding the ontology and registering the anti-atherogenic target state, for instance, as a disease model, we will have a much more clear and well-defined objective that we can optimize later. So this is all for now for me, but I'd be happy to continue and expand this conversation, offline, and I hope that Jose, we can continue this exploration and collaboration further. Thank you very much.
Thank you, Israel. Applause to her. As always, it's a great honor to have you, to hear you, and also personally, he's a great person. I can confirm that, not only professionally, but also personally. Thank you very much, Israel. So now I'm going to follow with the last part of the slide. Maybe in the team we can. Okay, so basically this is something that connects with the last part. I think it's very interesting because we take into account in our models that something that we knew intuitively, that is the cells are able to adapt and to react. And how is that possible? Because very probably there were a kind of machine learning inside the cell, intracellular. And those evidences have been recently published. This is in September, 1 month ago. 1 month ago, they were able to store 100 bits of information and perform machine learning with the molecules directly, intracellular. So this is machine learning, proteomics driven. And it has been published in Nature and Nature Biomedical Engineering. And this is key because it aligns with our last model. Sorry, again. This is like the sipping with the television, maybe. Something happened. I cannot move the slide forward. Okay, thank you. So actually, we released about something. I'm going to make a kind of a spoiler of the next slide. But we tried to make a huge study because we were able to control the proteomics and the transcriptomics at a cell level. Well, not to control, but small steps of controlling. Okay, maybe it's more honest to say that. But we were an epic fail, okay, as it say in the normal convention, when we try to simulate the anti-atherogenics process at the myocardium level, so intracoronary and microvasculature bed around the intracoronary. We failed, and we wonder why we failed. And maybe when we attended to the traditional convolution model that is in the normal artificial intelligence of, I don't know, AlphaFold and GPT, they probably use the normal convolution model, but maybe they have, of course, in the as industrial secret more things. But we find out that probably is because there are no true convolution in time. The cells make that kind of artificial intelligence. It's not artificial, it's bio-IA, and they are able to do that. But they interact in the real time, so molecules are not going to flip in each iteration. Numerically, when you do an iteration, the numbers flip. There is a glitch in numbers, but the cells don't do that. They remember everything, and mathematically, that's a convolution, a true convolution network. So we made a new kind of true convolution neural network that I call it Truco, because Truco in Spanish means trick. So Trucon, and with this new model, we were finally able to control inflammation at the cell net. Not only cell therapy, but cell net therapy. Now, okay, that was the trick. Sometimes it works, but yeah, now I have it. So the point is that, oh, it's a pity. But this is a real-time conversation of the cells. It's a pity because I should have expanded. There is ripples, small ripples in the waves, and this is a real-time talking simulation between many kind of cells. And the first window is proteomics. The second window is transcriptomic, which is slow. Oh, 1 minute. Okay. And then you have a stabilization of the signaling pathways and finally the markers. And this is the result. We were able to control the inflammation. The red is bad, green is not anti-inflammation, but at least control the inflammation in the myocardium. Well, let me tell you very fast a membership program. Why it's important? Because very probably, at least at the beginning, only billionaires and only developers are going to be in, maybe in the future, clinical immortality, but for now, cell network programming therapies. Or you are an early bird and you are in a membership program. Of course, I also oblige myself to do a social compensation of that. This is the curve of the membership. The prices are low at the beginning because, of course, it's like a normal investment. There are risks and nothing is guaranteed. But comparing with the prices in million euros, it's nothing because Cristiano Ronaldo and others, they spend like 1 million euros for monitoring. So this is, I think, this is for life. This is a unique payment. So, of course, you can split it in different quotas. But I think it makes the deal. Yeah, here you have 2 examples, but there are many people in the shadow wasting massive amounts of money. So I think that's admissible, the membership idea, to join with us. And contact, if you are an excellent student, please contact us. You know the excellency, the standards that we ask for, but contact with us. Also, if you are an intermediate, you know that you will receive 3% of someone who is interested in that. And finally, if you have a research group, we are very interested on that. Yeah, this is the last slide. Thank you. So, thank you very much for your attention. I want respectfully, in the 3 languages, say goodbye also. So, Peisho and Kaisi in the Kaishu. Y gracias, muchísimas gracias por su atención.
Thank you, Jose. We have our next speaker, who is group leader in cancer early detection at the University of Cambridge and is exploring senescence and cancer as key aging mechanism. We saw him briefly before, and he's here back now to have his presentation. Please give it up for Daniel Muñoz-Espín.
Okay. So thank you again to Jose and Maria Cordon and the rest of the organizers for this opportunity today. It's a pleasure. My name is Daniel Muñoz-Espín. I'm professor at the University of Cambridge. So these are my disclosures. I'm co-founder of YouthBio. Today I'm going to talk about the role of senescence in lung cancer and aging. After that, I'm going to present some novel therapeutics and detection tools that we have developed in my laboratory. And in the last part, I will present transient reprogramming as an anti-tumorigenic therapy. This is something very new. So first of all, let me please introduce cellular senescence to you. During the course of life, our cells are exposed to multiple sources of damage and stress. This accounts for replicative stress, DNA damage, oxidative stress, oncogenic stress. Our cells are exposed to viruses, bacteria, pollutants. And when these cells cannot repair this damage, they implement the senescent program. So cellular senescence is a process of terminal aging, and these cells are characterized by the implementation of a stable cell cycle arrest and a potent pro-inflammatory phenotype. So when these cells accumulate in tissues, they can promote a number of age-related disorders, including neurological disorders, cardiovascular diseases, fibrosis, diabetes, and also cancer. And we know by preclinical studies, by a number of preclinical studies, that if we target these cells with xenotherapeutic approaches, for example, senolytics, which are drugs able to kill these cells, there is an amelioration of all of these pathologies and even a reversion of these pathologies. So in collaboration with Professor Martinez Barbera at UCL, we have developed this mouse, p16FDR mouse, allowing us to track and to trace p16 positive cells, which is a main biomarker of senescence with a fluorescent protein, M-cherry, and also to ablate these cells with diphtheria toxin. And we crossed this mouse model with a KRAS-driven lung cancer mouse model because we wanted to understand the role of cellular senescence in lung carcinogenesis. What we found by using this model, what we found is that there is an accumulation of populations of senescent macrophages at the very early stages of carcinogenesis. These senescent macrophages upregulate multiple factors of immunosuppression, and we define biomarkers at the cell surface of these senescent macrophages, for example, FOLR2. What we determined with our experiments by pharmacogenetic approaches, by senolytic approaches, and also by immunotherapy, is that if we ablate these populations of senescent macrophages, then there is a dramatic reduction in the tumor burden in these lungs of the mice. The most important thing is that this correlates with an increased survival of these mice. This is a very long experiment of 2 years. The most important part is that even a 30% of these mice, even developing multiple precancerous lesions, they never progress to cancer. So this can be a potential, this is a proof of concept of a novel strategic therapy to prevent cancer and to intercept cancer in populations at high risk of lung carcinogenesis, for example, heavy smokers and aged people with smoking exposure. This also highlights, in correlation with the talk this morning from Omniscope, of the importance of a healthy immune system to tackle disease, and also of the importance of immunosenescence as a driver of carcinogenesis. We validated this with human samples from patients with precancerous lesions. We observed how these senescent macrophages accumulated in premalignant tumors, but not in the advanced adenocarcinomas. So this is a proof of concept that we can use this strategy to eliminate these populations of senescent macrophages which are carcinogenic. One interesting thing is that in naturally aged mice, what we observe in the absence of any oncogenic stress is that there is an accumulation in the lungs of the same populations of senescent macrophages, upregulating the same biomarkers of immunosuppression. And if we go now to aged mice and we induce lung cancer with orthotopic transplantation, what we have found now is that they accumulate these senescent macrophages which come, in the particular old mice, they come from non-classical monocytes from the bone marrow. And these populations of non-classical monocytes have an array of biomarkers which are conserved with factors of bad prognosis of lung carcinogenesis in humans. So we think these are the bad cells that we have to target in therapeutic approaches, and we are doing now this proof of concept. Another thing that we have found is that if we inflict damage in the lungs in normal mice and also in middle-aged mice can recapitulate, for example, people 50 years old. What we found is that if we inflict damage in the lungs, there is a higher tumor progression in the case of the middle-aged mice when compared to the young counterparts. The conclusion of this is that damage and aging creates a permissive niche for the onset of cancer and for the progression of cancer cells. And then these mice have a very reduced survival. The cellular type that accounts for this phenotype is, again, senescent populations of cancer cells and cells of the tumor microenvironment, including macrophages, that are able to secrete TGF-beta ligands. And what we found in this study is that if we target the TGF-beta signaling with an inhibitor, we can rescue this phenotype, and then we can reduce dramatically the tumor burden and increase the survival of the mice. And we have recently published this in Nature Aging. This has been accepted in Nature Aging. Now what we have done is using more physiological models of lung cancer with this KRAS-driven lung carcinogenesis in mice with oncogenic KRAS activation. And we treated these mice with diphtheria toxin to reduce the numbers of senescent cells. So you can see how the senescent cells in red are reduced, and this correlates with a dramatic reduction in the tumor burden and in the number of cancer cells in the mice. So the conclusion of this experiment is that senescence is protumorigenic in the context of aged mice, and that we have now to define what are the therapeutic targets of these cells in order to develop more efficient medicines. So now I'm going just to show a few examples of drugs and therapeutics developed in my laboratory as a proof of concept. We develop nanocarriers, drug delivery nanocarriers to target senescent cells. In this case, chemotherapies, you can see how they can induce senescence in this blue stained tumor that you can see in the picture. So when we treat mice bearing subcutaneous tumors with chemotherapies, we can arrest, establish the tumors, but only when we combine chemotherapies with therapeutic nanoparticles to target senescence, we can completely eliminate the tumors. These nanoparticles targeting senescence not only work in the context of cancer, but also in lung fibrosis. Senescence is a factor that strongly promotes lung fibrosis. As you can see here in this 3D rendering of these lungs, these gray areas, which are fibrotic areas. And when we treated these mice with therapeutic nanoparticles to target senescence, you can see how the tissue is completely regenerated in the lung, and this also recovers the pulmonary function of the mice. We have developed as well a prodrug able to kill senescent cells that we validated in this model of lung carcinogenesis, almost completely reducing the tumor burden in the mice. This prodrug to target senescence was also tested by the Lyfe Foundation, and they found that this was synergistic together with rapamycin, with the activation of the telomerase and the transplantation of hematopoietic stem cells to increase the lifespan of mice. We have developed also detection modalities for the assessment of cellular senescence. These are nanojags, which is a sensor able to, with a photoacoustic tomography property, to determine the senescent burden by imaging. And this works in mice, in tumors, when treated with chemotherapies and undergoing the accumulation of senescent cells. This is how it works, and you can see in this video how in the right part there is a tumor which is positive for the accumulation of senescent cells. We have developed as well another intervention which is non-invasive for detection and assessment of senescence in the urine. And this works in the context of chemotherapy-induced senescence in cancer and lung fibrosis with colorimetric assays and also with spectroscopy methodologies. And just to finalize, so this is a summary of my talk. These are the therapeutics we have developed in cancer, in aging, and also in lung fibrosis. This is the company we have co-founded. I want to thank Ken Scott for being an advisor of the company. We have developed a kit. And just to mention, just 30 seconds, that we explore transient reprogramming. We hypothesize that maybe if we express the Yamanaka factors in cancer cells, this can result in benign tumors on an increased tumor burden in the mice. But what we found is that by expressing the Yamanaka factors in transient reprogramming, what we found is that in the left part you have a normal tumor, and in the right part a tumor where the Yamanaka factors are expressed in a transient manner. And you can see how this results in apoptosis and in the death of cancer cells. And this was also confirmed by experiments with a KRAS-driven lung cancer model. And you can see there how the activation of the Yamanaka factors, in particular OCT4 and KLF4, results in a reduction of the tumor burden. So this is a proof of concept, and we want to move this to early phase clinical trials. So the conclusion of this study is that the transient reprogramming in cancer cells results in apoptosis. So this is an anti-tumorigenic mechanism that we want to move to early phase clinical trials. And the take-home message of this talk is that now we are in a position of privilege to implement these senolytic therapies and transient epigenetic reprogramming for the first time to ameliorate aging and to promote rejuvenation and regeneration. Thank you very much to the people in my laboratory, to all of our sponsors. Also, particular thanks to this Darley Sands scholarship. And also, I will be happy to hear from any investors or any pharmas or groups interested in our research. Thank you very much.
Thank you very much, Daniel, for that. And as Jose also mentioned earlier this morning, we had a supercentenarian here in Spain who became 117.5 years old, unfortunately died last year, but Natalie sequenced her, so she probably has a lot of exciting information on this too. But enough about that, let's give it up for Natalie Coles.
Hello, everyone. My name is Natalie Coles, and I will just give you a brief introduction of myself while I put up my slides. So I have been doing supercentenarian research for about 17 years now, and I'm mostly on the clinical side of the research. So that involves mostly coordinating and getting the samples to send them to other researchers to do what they need to do. So my talk is titled Supercentenarians and Further Advancements, and specifically this talk is about the case and life and findings of Maria Brañas. So this is a picture of Maria Brañas, the day that I actually took the sample, so you can kind of get an idea of what kind of shape she was in for someone who was 116. And as you can see, she's doing fairly well. I mean, she also looks younger, she acts younger, or acted younger, and was very aware. And where she was at the time when we visited her was in Olat, Girona, Spain, and this was on May 17th of 2023. So who was Maria Brañas, and why did we want to study her? And the answer is, at the time, Maria Brañas became the world's oldest verified living person on January 17th, 2023, following the death of the previous title holder, Lucille Randon. She held the title until her death, till August 19th, of 2024. And Maria Brañas lived to her advanced age, and what made her so interesting was not only did she live longer, but in order to do that, she bypassed cancer, dementia, cardiovascular disease, and demonstrating a separation between extreme longevity and the typical health decline associated with aging. And she became an example of healthy aging to the world while she kept the title of the world's oldest person. So this is the team. So as many of you may or may not know, we often get a lot of false claims. So in order for me to be able to conduct this research, we need for the supercentenarian to be validated. So this was a very special team because the person who validated her at the time was currently the validator for the Guinness Book of World Records, and his name was Robert Young. And then we had Dr. Manuel Esteller, who conducted pretty much all the research on this particular case, and he is actually based here in Spain. He is director of the Cancer Epigenetics and Biology program at Bellevue Biomedical Research Institute. He's also a professor and a physician. And then I myself was able to get them the blood sample which they use for most of the analysis. And my title currently is Director of Supercentenarian Research at LEV Foundation. I have also and the Gerontology Research Group, and I have previously published with UCLA, Stanford, PLOS1, and now with this particular case with Cell Reports and Medicine. So what samples were obtained from Maria Brañas? Next slide, please. So what we were able to obtain from Maria Brañas was actually very significant. It was more sampling than we have ever conducted, or that I have ever conducted in the past on any other supercentenarian. So this is why this is not just a very special case, but it's also historic. So we collected a total of peripheral blood, saliva, urine, and stool at different times. Most of the analysis from this publication were performed on the blood material obtained at the time of her being 116 years and 74 days. So what did we find that contributed to her longevity? So during the blood analysis, one of the things that we found was that she possessed uncommon genetic variants, and this is related to a strong heart, brain, and immune system function. She also lacked most genetic risk factors that are common in age-related diseases such as Alzheimer's and cancer. This is a really big deal because we see that most people who get these illnesses get them as early as 70 or 80. So for her to be 116 and never had cancer or Alzheimer's, It's a big deal. And the most noticeable findings pertain to her telomeres, her B and T cells, and the structural chromosomal variants. So the B cells are important because if you notice this chart right here, you'll see that Maria Brañas, what represents the B cells here is that really large chunk of red, okay, off to the left there. And so B cells are age-associated. B cells normally increase with age, and these were very abundant in Brañas's blood. That makes sense because of her being as old as she was. But what I will say is I don't think that we feel that we know enough about this, because there are some hypotheses that think that anything that is above normal might be something that theoretically could have some benefit to it, considering that they live so long. So I think that when it comes to these B cells, we need to study them a bit more to know that how that might have been useful or extremely more significant than just what we already know with Maria Brañas. But in summary, while some of her B cells showed the typical signs of aging expected in supercentenarian, other aspects of her immune profile, including the presence of a big amount of T cells, was also very important, because those are important for fighting off infection and just recognizing them quickly. So here we see that, the combination of expanded cytotoxic T cells and robust mitochondria function pointed to exceptionally resilient immune systems, which protected her from age-related diseases and other factors. She also had structural variants, and that was also very significant. I won't get too much into the technical aspects of that because that's all in the publication, and I didn't memorize that. But that's important because what it is basically that it is protective. We see a lot of DNA damage, and this can cause more differences in the way that the sequence is structured. And by having these particular variants and protective mechanisms, it protected the structure of the DNA. So with the microbiome, they were also able to find a lot of different things about that, which is that she basically had a very youthful microbiome. And her gut microbiome diversity and balance were similar to those of a young child and not normally associated with an elderly person. She also had, it also reduced inflammation, and another thing that was significant about Maria Brañas was that she also adhered to a Mediterranean diet. So lots of fruit, lots of vegetables. Many of you might have seen in the newspaper that she was also known to eat 3 yogurts a day, and with no sugar. And this contributed to having a high rate of positive bacteria that was much higher than people her age or younger. And so this also contributed to having a very resilient immune system. We also did urinalysis, and her urine and other samples showed retained hypermethylation of repetitive genetic elements that typically lose methylation with age. So this is a protective mechanism, and she showed more of this than what we normally see in regular patients, which may have contributed to her genomic stability and the protection against disease. Another really interesting thing that we were able to gather from Maria Brañas that previously we really had no knowledge about, and we still don't know enough, was that she was exposed to 2 pandemics. So not just the Spanish flu as a child, but she also was exposed to COVID-19 when she was 113. And what was really interesting about Maria Brañas is that not only did she survive COVID, but she actually was asymptomatic. So there were a lot of people that we saw youthful that were passing away, and Maria Brañas got it at 113 and asymptomatic, was totally fine, did not get hospitalized, and overcame it very easily. So unfortunately, like I said, we don't have enough data, but we suspect that this plays a huge part in her longevity, because as you now start to put together the pieces of the findings, we see that everything is conducive to that kind of outcome. We see that she had an exceptionally large amount of T cells, which is kind of the soldiers of the immune system, who are able to recognize and attack quickly, and that she had an abundance of. We also see that she had a large amount of B cells, and even though those accumulate with age, they're still part of the immune system. So this was very, very important, and not only was it important to the researchers, it became extremely important to the Spanish government. Here in Spain, Maria brought a lot of attention to the fact that the elderly were a very vulnerable population and that they were not being protected enough. And she actually became an advocate for the elderly and participated in kind of an advertisement and helping promote vaccines for the elderly and in nursing homes. So one thing we also noticed, and what was she said to have among traits of her personality, was that she was a very generous person. She was kind, she was smiling all the time, and she was very grateful for her title of world's oldest person. And one of the things that she also attributed to her longevity was the philosophy for a long life included an orderly lifestyle, a balanced diet, and staying away from toxic people. And so I think it's something to sort of take into consideration. If many of you here in the audience want to live to be a supercentenarian, we believe a lot of that is genetic, but there are things that you can do to not only honor Maria Brañas, but also honor yourself and find ways to mitigate things that contribute to accelerated aging. So diet, lifestyle, and just making sure to just be happy and stay away from toxic people. So that's pretty much the majority of my talk, and from what I understand, we're running a bit late, so I can answer questions at the coffee break, but if any of you would like to know more or get into the real details of the science on the technical aspects, you can find the actual publication with the, like I said, the detailed technical aspects of the findings in Cell Reports. And also, if any of you would like to contact me for collaborations or just to know more, or if anyone is interested in getting involved, we do need and we're looking for people who are interested in assisting with validation here in Spain, just because it's an area where we don't have enough researchers, and we would definitely like to give credit to all supercentenarians if they're able to get validated. And that's all. Thank you for listening.
Thank you very much, Natalie, and thank you also to Jose and Daniel.
We have a fantastic session about Madrid and why Madrid is the most longevous city in the European Union, and Spain the most longevous country in the European Union. And for that, we have our Master of Ceremony, all the way from Sweden, but she was in Switzerland and now she goes to Dubai, Sabine von Gafken.
Jose, thank you. Thank you. Great to see that many of you are back. I hope you're energized. We have a really interesting, I would say afternoon, but early evening ahead of us. And this next session is, like Jose mentioned, it's about Spain and Madrid and why, or also congratulations to, that it has the highest life expectancy in Europe, according to certain studies. Now, I just want to mention iconic author Hemingway once called Madrid the most Spanish cities of all cities, swooning over its people, over its climate, and over its refusal to sleep. So one wonders, could these be the key ingredients? No sleeping, lots of tapas, lots of early mornings, siestas, fiestas, to why the Spanish people are said to be the most long-lived. Well, we have three experts who will dive into maybe not that specific topic, but topics around to what makes Spain and Madrid so vibrant and youthful. And first up, we have Lars Hartenstein, who is from partner at McKinsey and Company, and they have released a research that is Healthy Cities, Healthy Growth, Spain's opportunity to shape the future of the longevity agenda. So let's hear more about this, and I hand the word over to Lars. Give it up for Lars.
Yeah, thank you very much. The McKinsey Health Institute is an independent institute within McKinsey that looks at underinvested areas of health. And one of those is healthy longevity, and I'm going to talk about this now. To begin with, talking about the healthy longevity in Spain and Madrid and asking a German living in Paris, I feel slightly miscast, given that the healthy longevity here is higher than any of the places I come from, so I'm not sure what I can exactly teach you here. But anyway, I've been asked to do that, so I try to speak to the subject nevertheless. So I'm going to do three things. I'm going to talk briefly about healthy longevity in a way that is overall understandable and combine some different angles, and then about Madrid and Spain in particular, where the status is there right now in terms of healthy longevity, and lastly, what one might do going forward. Overall, I have a background in medicine as well as many years ago in economics and political science, so don't be surprised that I'm going across different disciplines a little bit as I'm speaking about this. So, just some basics. There's a great success story in terms of life expectancy if you take it from the global level, right? So there's a 20-year increase in the 1960s. However, we are paying an incredibly high price for this. For every additional year of life, we are spending 6 months in less than great health. That's a terrible price to pay on some level. So imagine that every additional year we are spending was actually a year in good health. That's what this is about and what I'd like to explore with you today. So if one can say what we want to do is that we want to square the life curve. So the normal course of life is that we have a relatively long period of decline where, you know, you have restricted brain function, you may not be able to remember your children, people may be incontinent, back pain, all sorts of things that make life less worthwhile. But the idea is, can we live as long as possible before in good health? And as McKinsey Health Institute, our claim is that yes, it's possible. We can add 45 billion years of higher quality life globally. That's 6 years per person just by knowing what we already know how to do. So just to connect a little bit some of the different talks we have been seeing here during the conference, right? There are three different angles on healthy longevity. First of all, there's the cellular level, the hallmarks of aging we've heard about today, where the intervention in the end is about, are we having therapeutics, are we having new drugs at some point on the horizon, right? That is a research question mostly. Then there's the individual level. Yeah? The individual consists of 30 to 40 trillion cells, and that has to do a lot with what we do every day, what we put into our bodies, what we are exposed to in life, yeah? How we move, also of course healthcare, even though it's just one of many parts, and also what's our overall state of being. And then I'm going to get to that when we talk about the city, is a population level, right? On a community level, on a city level. But I think these three frames are important to kind of also organize a little bit the different things that we're hearing when we talk about healthy longevity. So this, just as a reminder, we've heard that, and I'm not going to belabor this too much, but there is, from a science perspective, a tremendous increase in the research on these hallmarks, on the biomedical perspective on aging over the last 10 years. So now, let's talk about Spain. So Spain is doing terrifically well if you look at healthy longevity. Now, if you only look at the slide quickly, you say 70 plus 1 years, you think that's not too much, but that's a healthy life expectancy. That's how many years you can expect in good health, right? And there, if you take a global level, Spain is doing very, very well, in the European Union leading, and 71 plus 1 years, that's really, really good. 86% of the overall life expectancy from 82.7 years. It's a bit more now because those are globally comparable data from 2021. So if you now look at cities, Madrid holds a very privileged position. So therefore, I think you need to teach me something. Those of you that are living here, many of you, what to do about this. But Madrid is essentially leading on healthy longevity globally. I think one way to look at this, rather than going like in a deep causal analysis, it's a little bit more like Las Meninas by Velázquez in the Prado, which is an accomplishment of a huge cultural achievement, if you want. In the same way, the healthy longevity doesn't have like individual causes, it hasn't happened by design. Las Meninas is basically depicting the accomplishment of decades and centuries of court life in a painting. And so the healthy longevity results is a cultural achievement where many things, diet, Mediterranean diet, ways of life, small portions come together and produce that. It hasn't happened by design, it has emerged by and large. Of course, there are also initiatives and so forth, but that would be my perspective on that. But it's a very fortunate starting position. So now, investing more in healthy longevity has enormously high returns. And the analysis that we are showing here that we did globally, and here we're showing some of the Spanish numbers, is basically only predicated on intervention that we already know how to do today. Yeah? And so we can add, by only doing that, for Spain or also the world, about 20 years of healthy days per person a year. Right? And also has enormous GDP impact. That 184 billion US dollars of GDP for Spain alone is what can be achieved there. And the return on investment from a societal level, even for a city or for a country like Spain that is doing very well, is very high. So healthy longevity is a good business for a country. To invest in healthy longevity is a good business for a country. So, and now if we look at where does that come from, what is a disease burden that can be addressed with known interventions? Nothing fancy, no drugs, nothing, only things mostly that we already know how to do. So number one is surprisingly smoking cessation, even though smoking rates have gone down, but it's still such a killer. So very, very important. And then the next one, if you combine a theme around the next one that is collectively bigger, I would call it metabolic health. The metabolic health is really an incredibly important driver of health. So further improvements in metabolic health that lead otherwise to heart disease, diabetes, and so forth is very important, but also treating the complications of metabolic health for those that already have complications. So those are the low-hanging fruit, so to speak, that one can think about. And happy to talk offline also, but we also published on this where the value comes from, but it's essentially a labor or an employee-based perspective, yeah, where people live longer, can work more and so forth, but without making any undue assumptions vis-a-vis the current legal situation. So now, who of you thinks that cities are an important driver of healthy longevity going forward? I think I still need to do some convincing here, so I'll do it, yeah? So cities are incredibly important, arguably the most important composite driver of health, because the majority of the world population is going to live there, and especially the people that are older than 60 are going to, with majority, live in cities going forward and already today. And that's also where there are enormous powerful stakeholders that can change our life world, employers and so forth, that can influence how we live, how we eat, how we move. And there's enormous power, therefore, in cities to change things for more healthy longevity. And there's enormous disparity within cities. So I don't have the numbers for Madrid on this one, but like there are some cities, London or Chicago or so, where there's within one city, there is 30 years of difference in life expectancy. So the dimensions are different, but it's more or less like this in every place. And the difference is always an indicator, therefore, that there's potential to do better. So now, This is the one slide that our team has put together where I'm going slightly the area outside my expertise, but there's a lot going on in Madrid already, and many of you will recognize the initiatives depicted here. So there are a lot of institutions that are influential in the space of health that if one to change things going forward, there's therefore an infrastructure that can be supportive for healthy longevity. I don't want to put any words in anybody's mouth, but that can contribute to any efforts to enhance health and longevity. And that's why cities have an enormous potential that some other places don't necessarily have. So what can cities do about this? So let me just first do theory and then some practice, or not theory, but like a little bit of structure. There are essentially 4 things that cities can do. Number 1 is public awareness and health literacy. Yeah? That can be role modeling, this can be campaigning, this can be behavioral interventions, but that's number 1. Then number 2 is what I already alluded to before, is cross-sector mobilization. If the big stakeholders in a city really are aligned to drive something, whatever, be it a change of diet, change of stress or sleeping patterns, whatever is identified, or smoking was identified as a critical driver in that particular cities, can be enormously impactful. If I go clockwise, policies and regulations, that's maybe the most discussed in some ways. Sometimes a little bit more on a country level, but there are also, of course, regulatory aspects that a city can control. Where can you smoke? It depends a little bit city by city. Where can you do different things? Then lastly, infrastructure design. That obviously takes longer time, but especially with bicycle pathways and so forth, other things that promote active mobility, that is a very, very dimension. Also social health and how people come together, very important from an infrastructure perspective. So now, let me just end on a couple inspirational examples, or examples that I find interesting, where cities have come together to really do something different. And one I think is interesting from Europe here, is a little bit through different world regions, in Amsterdam, where there was a decided effort to do something about childhood obesity. Childhood obesity, I don't need to belabor the point now, but it has extreme long-term perspectives, right? So I think if you want to do something for your child, the metabolic health of your child, that's a very good thing to look at. And Amsterdam has really had a cross-sector mobilization effort to do something about childhood obesity in school, and also with very good results. Singapore is overall a very important example because they have succeeded to also in the health system go a little bit more from a treatment to prevention, where there's strong incentives for preventative treatment, for example, no copay for preventative treatments while there is copay for treatments. Yeah, so really a shift in the priority with the health system, very interesting. But to kind of pick something out that's very city specific, over a decade now, a step challenge that has by now been amplified to other areas, that has really increased the physical activity of people, and very importantly also gotten people who are not physically active into more physical activity, as opposed to only harnessing a few people that are already physically active to kind of participate in some kind of challenge. So getting people in a different physical activity status at population level. Singapore, very nice example. They've also done other things. Another inspirational one, I think, is Abu Dhabi, also something that I personally know something about, or from personal experience, a place with very poor metabolic health and high obesity, but where the top level of the stakeholders have decided to really do something on this in a 360-degree way, and really looking at all of the different possible dimensions, what kind of food is being served, how are people being educated, what kind of role modeling do we need, what are the regulatory measures that we need, what is happening in schools, what's happening in the households, to really have many, many, many different interventions at the same time to really make a difference on, in this case, one area, arguably the most important one, also for Spain, or for Madrid, based on the analysis that we have done, which is metabolic health. So let me just close here. I'm very happy to also have conversations afterwards in the margins, a topic that I'm very passionate about. And maybe last comment is sometimes one feels those looking at healthy longevity individually are getting stressed trying to chase healthy longevity, maybe a little bit, but sometimes it feels a bit like, chasing for a butterfly or so, maybe, and the more you chase it, the more difficult it is to get. So maybe sometimes it's also good to sit down and have a good glass of something, maybe, and that may be the right recipe at times. So I think important not to be too stressed about it on an individual level, but on a population level, very important priority area to look at. So with that, I pass on the microphone.
Thank you so much.